This is my presentation title, Characterization of a highly polymerized Alaskan binder. This is part of work of one project funded by Alaska Department of Transportation and Public Facilities, and which we completed last year. And here's the outline of today's presentation. I'll give a brief introduction and then talk about the both asphalt binder characterization and also performance tests of asphalt mixtures. And I will also talk about the field evaluation. And at the end, I'll provide the conclusions and the recommendations. In the past decades, asphalt binders have been modified using a wide range of polymers modifiers or technology to achieve the desired properties. And the polymer is the most commonly used asphalt modifier. So what is a high HPAB, highly polymerized asphalt binder? So basically, for this type of binder, it has polymer concentration is very high, and about 7% of asphalt binder. So the HPABs have been increased used to address rotting and cracking concerns of flexible pavements under extreme climates and high traffic. And this paper published in 2020 basically give a very good critical review of current status of studies and also engineering practices on HPAB. So I just copied several tables from this paper, including the both binder and the mixture experience, and also case studies by different agencies. So according to this critical review, the benefits of HPABs used in warm regions or busy traffic areas have been identified by a number of studies. So our study could serve as a complementary work of current practices to look into the HPABs in cold climates. Alaska has been using HPABs in a number of paving projects in recent years. However, there has not been systematic characterization and performance data development for this type of material. So the objective of our study is to fill the research gap by systematically characterizing the HPABs and mixtures and identifying the performance benefits of these materials through lab testing and field section monitoring. Okay, so in this study, we selected the unmodified binder PG52-28 and the other three types of HPABs currently used in Alaska. And this table summarizes the loose mixtures we collected from the paving projects and for performance test of mixtures in this study. This slide summarizes the tests we conducted for binder characterizations, including FTIR in the fluorescence microscopy for chemical and morphologies study, and also other tests to evaluate the rheological properties and low temperature cracking and rotting resistance, and also fatigue resistance. And this slides summarize the performance tests for mixtures, including the hamburger wheel tracking test, integral tension testing to evaluate low temperature performance, and also semicircular bending test to evaluate the cracking resistance. Okay, so here is the result from FTIR Spectrum, and so you can see here significant difference can be observed at the wave numbers from 400 to about 1700 wavelengths. And here this is a larger view of this during this wave number. And also if we compare the this type of this PG64-40 with the unmodified PG52-20A, we can see unique absorbance peaks were found at around here about 990 and also about 780. So basically, this represents corresponding to carbon-carbon bonding and also carbon-hydrogen bonding in this highly modified binder. And this is the result from the Florence from FM and morphologies of HPABs. And so you can see for unmodified binder, basically there's only just one phase can be observed. However, if we look at the other three types of HPABs, a biphysical physical structure can be found, and you can see for this PG52-40 and 64-40, basically polymer formed a continuous phase, implying adequate compatibility between polymer and asphalt. And it's very clear the polymer phase was a dominant phase for the highly polymerized asphalt binders, especially for, you can also see from this PG52-46. So here, this is the G-star master curve of the studied HPABs at the PAV agent state, as well as the unmodified binder PG52-28 at a reference temperature 50 degrees Celsius. The unmodified binder PG52-28 showed the highest G-star data. In other words, the unmodified binder was the most stiff, so it was generally believed that the softer asphalt binder at higher frequencies or intermediate temperatures would perform well in terms of fatigue cracking resistance. And here are results of percent recovery values at 3.2 kPa for studied asphalt binders, and also the critical cracking temperatures from a low temperature performance evaluation. So as we can see from this figure here, the unmodified binder showed nearly no recovery, less than 1% recovery, but the others had a very high percentage recovery, which implied they are more elastic at the high temperatures. And here in this table, we summarize the temperatures based on the criterion from the BBR, the creep stiffness and the M value, and also the cracking temperature directly measured from ABCD device, is asphalt binder cracking device. So it can be seen that all HPABs has much lower critical cracking temperatures, and though there are the difference due to the mechanism behind of testing methods. And this is the Hamburger-Willow tracking test results for mixtures, and so you can see the use of HPABs improved the rotting resistance the rotting resistance at a noticeable level, regardless of the high-end pitch of asphalt binders. And so we see mixtures with unmodified asphalt binder show the higher rot depths than those with modified asphalt binders. Here we compared the cracking temperature and the low temperature cracking temperatures and compared with pavement temperature. And here, basically, I kind of summarize all in one slide, but really there's a comprehensive analysis behind this slide. Because so here daily air average air temperature we collected from the online climate data from the weather stations in Fairbanks, Alaska, and basically we look at the past I think the past 10 years data, and we select this within here. This is the kind of coldest winter in the past 10 years, and here the TPAV at 0.01 millimeter, which in this black line, that's the predicted pavement temperature based on this TEMPS software temperature estimate model for pavement structures. And the other lines, okay, the other lines basically are predicted cracking temperatures from low temperature performance tests. So basically, we use IDD test to obtain the creep compliance curve, and also the indirect tensile strength, and then we compared the development of thermal stress with tensile stress and to predict the cracking temperature. So then by compare the cracking temperatures for the mixture used for the pavement, and also pavement temperature due to the weather conditions, and we can predict if there's any cracking occurrence. So as we can see from here, so for this PG52 mass, the mixture for PG52 mass 28, suddenly they are cracking low temperature crackings, but for highly modified binders, and they should perform well. And we also did a field survey in the summer of 2019 so these are pictures from different paving projects in Alaska constructed in different time. So overall, you can see they perform well. But you can also see, because most of paving projects with HPABs are being constructed in recent years, and so a long-term performance monitoring is needed. So in addition, we dig out the LTPP database to see if we can get some information regarding long-term performance. And so this is the test section we used from LTPP database. And so both sections are in Canada and constructed back in 1996 with a similar highly modified binder grade PG52-40. This table basically summarizes some survey data. So you can see both basically since it's constructed in 1996, and both sections showed no longitudinal cracking after 11 years of service from 1996 to 2007, and also no fatigue cracking during the first 6 years, and even they have they had a rotting issue, but the rot depths no higher than 10 millimeter after more than 8 years service. So most importantly, both section has no transverse crack. So so by checking these sections, the pavement use HPABs performed well. Okay, so here's conclusions and recommendations for this brief presentation. HPABs showed a significant different morphologies than UAB with biophysical structure. Lab testing and field evaluation results indicated the HPABs and the mixtures outperform in terms of rotting, low temperature cracking resistance. Limited experience of demonstrated pavements constructed with HPABs performed very well after years. However, more years of field monitoring and data connection are recommended. And also better tools are needed to correlate lab performance and field performance under real climatic conditions. For this study, I would like to thank Alaska Department of Transportation and Public Facilities and the Center for Environmentally Sustainable Transportation Cold Climates for sponsoring this study. And also the presentation today basically is from this paper published in this early this year. And also we have several other papers and also this comprehensive report if you would like to get more information. Thank you very much. That concludes my presentation. I was kind of rushed. I'm trying to make sure I don't overuse the time. I think I'm good. Any question? I think within my time slot, I think I can have like 1 or 2 questions.